the education of so many people in the wireless field. It's a true passion of mine. I think it's how God wired me to be passionate about this field. And so I'm honored to be here, and I'm excited to share with you a new theory that I think is going to be in all of our textbooks in 10 or 20 years, or hopefully sooner. I'm talking about a new theory called waste figure or waste factor, and it's been a 15-year journey. I had a brilliant student named James Murdoch, and I've just started the timer, and he wanted to solve a perpetual motion machine. He was a really brilliant guy, and I couldn't convince him to stay for a PhD, but I did convince him to figure out how power is wasted and why a perpetual motion machine can't be built. And I got him to look at circuits and systems, and I'm now, after a 15-year journey, ready to go public with this. And I think it's really, really powerful. I'll show you why in this talk. So energy consumption, we heard Eric talk about it. I'm really happy to follow Eric Lang, who's on our board at NYU Wireless from Ericsson. And he mentioned how carriers, 2% of their gross revenues go into the electricity bill. Energy consumption is vital. And right now, the industry, our industry, the wireless industry, the ICT industry, is only about 3 or 4% of the global power consumption. But in 2030, it's going to be over 20%. And that's even before the AI ML craze, which is huge power consumers. So this is a really important, and I want to look at the radio access network where the hardware is sold, both in the infrastructure side and the mobile units. And if you look at the wireless carriers, and there's about 400 or 500 big carriers around the country, all involved in carrying out the service that 4.5 billion people get on their cell phone every year. 76% of the power consumption is in the radio access network, the base station infrastructure, and the mobile units. I'm going to show you this new theory, waste factor, accounts for any circuit, any system, and even multi-user source-to-sink communications, including the entire RAN network. I believe this is the world's first unifying metric for quantifying and therefore optimizing power consumption for not just our industry, but the computer industry and anything that has a source to sink in an information flow. It all started in this 2011 paper, which actually kind of started the millimeter wave revolution. In here, I predict millimeter wave mobile. And in the back of this paper, in the proceedings, is the beginnings of this waste factor theory. It's very mathematical and very crude. And then a little bit later, my current generations of students started to refine it. And we presented this at GlobeCom last year. It won the Best Paper Award for evaluating the power efficiency in any cascaded network. And in about 2 weeks at the International Microwave Symposium, Microwave Journal will be featuring our first comprehensive paper on waste figure and waste factor for the world. And this will be open domain. I wrote the paper asking them to make it public for the world. And we will soon, in about a week, be publishing a lot of what I'm going to talk about here in the Open Journal of Communications. And I'm going to make that available because it's so vital for our planet that we all rally around some figure of merit. I think waste figure could be it, but if not, certainly research into this will spawn a way to properly characterize the power. And I want you to realize that this has been a 15-year journey, and there's a fundamental superposition law that James and I figured out back 15 years ago. It's well known. We teach it in sophomore circuits. And that is, any active device has 4 power components. In order to figure out the total consumed power, there's the power input, that's a signal input, usable signal. There's an output, usable signal output. And then there's the total power consumed by that device. And then if that device is not on the communication path, we can count the non-communication signal devices, the ancillary devices, as non-path power. So there's really 4 components: input, output, power consumed, and that includes power wasted, and then all non-path components. I'm going to set that up in a little bit more detail, but the bottom line is we can use superposition of power to figure out how much power is wasted from the source at the left to the signal at the right in a very systematic, very elegant way. In fact, the elegant way was inspired by Harold Freese when he invented noise figure or noise factor in 1944. We all know from our communications theory that noise factor looks at a thermal noise source at the left and then looks at the additive noise component by component from the source to the sink. The beauty of noise factor is it allowed a systematic model to quantify additive noise in a cascade, assuming linearity. And this equation at the bottom shows that the additive noise of each component is related to what he defined as F, noise factor, -1 times the gain of the noise at the input. And if you look at the math, which we did, you go back and look at his 1944 Bell Labs paper, and you see systematically he's able to find in each device in the cascade the additive noise along the cascade from source to sink. He comes up with the famous result at the bottom that a cascaded system has a noise factor that's equal to the sum of the noise factors divided by the gain of the previous stage is referred to the input. In fact, this is a famous equation we all use and we all know. We heard the keynote speakers yesterday use this in figuring out their devices and link budget in satellites. So this is very well known. Well, we did the exact same mathematics, and instead of looking at a noise input, we looked at a power input of a source, a desired signal, a desired source, and we looked at the incremental wasted power, that is power that's not in the signal coming out of each device of the cascade. Using the exact same math, we defined waste factor as the power consumed divided by the power output. This is a very key observation. It's very simple. It's actually efficiency in the old way of the original circuits when PAE was defined. I'll get into that later. But the bottom line is if you know the gain and the efficiency of any device, active or passive, in a cascade, we can come up with this equation at the bottom that gives us the wasted power is related to this waste factor, which is defined as the output power, consumed power over the output power. Very important here. Waste factor can be measured because you can measure the consumed power and you can measure the output power in the desired signal. So waste factor can be measured and it can be modeled. And when you do the same math that Harold Freese did 80 years ago, you come up with the exact result of a cascaded system where instead of additive noise, we now have additive wasted power, where a W of 1 means all power comes out into the signal. All consumed power comes out into the signal for a waste factor of 1. And W greater than 1 means there's waste. Just like noise factor, an F of 1 means ideal, no additional noise added. W of 1 is no additional wasted power along the cascade. All the consumed power goes into the signal. So a W greater than 1 means you're getting power wasted along the cascade. And voila, using the exact same approach, which we talk about in the Microwave Journal article that'll be public in 2 weeks, you get the same kind of result of a cascade of a system, a linear system. And note that here, the output power is what's important because you measure consumed over output. So here, waste factor refers to the output. So you can see the gain of the component closest to the sink, G sub n, closest to the right. The power in the output stage is most important for determining power efficiency or waste factor. So in 1944, we have something that's in all of our textbooks. In 22, 23, we came up with waste factor, which I believe will be needs to be in all the textbooks and all the data sheets for reasons you're going to see. So this is a very elegant way to look at a cascade and the total wasted power. Now, here's what's amazing. You look at how we do things in the circuits world. You look at the power added efficiency originally defined by Sweet in the late 80s, early 90s. And you see that the power added efficiency originally used 30, 40 years ago was the output power, that's signal output, divided by the DC consumed power plus PN. And when you flip that around, you see that the reciprocal of that is exactly what waste factor is. So the original PAE definition is actually the reciprocal of what we're defining waste factor. And then PAE morphed into a definition that looked at the output minus input. That's kind of the additive gain. And when you look at the additive gain, PAE, we show very easily that the waste factor is simply related to the reciprocal of PAE2 by this equation on the right. And if you notice for a high gain amplifier, 10 dB or more, that this term PN is going to be much smaller than PDC, so that's about 1. And you also notice the term on the right, the gain's going to be big, so 1 minus something is also going to be close to 1. So you can see that W is very close to both current definitions of PAE. So this is a way to unify the way circuit designers look at power efficiency in amplifiers. And for low noise amplifiers, similarly, you can find a W, the waste factor. It's about 1 for near saturation. We showed that in a paper a couple of years ago. And then operating in a linear range, you could use existing figure of merits and figure out what the waste factor is for an LNA. We've also done this for ADCs and DACs. We're going to publish that in about a week. We'll make it open. But the bottom line is W, this waste factor, is something that, ideally has nothing to do with the actual input or output signal levels. Here, it's just, if this device is linear, you don't need to know the input or output signals. And the trouble with a lot of figure of merits today in the circuit world is they're very much dependent on input or output levels. You can measure the total consumed power, but if it's linear, ideally you can get a waste factor that doesn't depend on input or output. Let's apply this waste factor theory to an example of a source to a sink in a homodyne transmitter. This could be an IoT transmitter. And here you've got, let's see, baseband, mixer, and RF are on the signal path. So these are going to be functions of W. And then you have an oscillator, which is not on the signal path. So that'll be non-path power. So to figure out the total power consumed, we'll look at the signal path and the efficiency of source to sink, and then we'll add all the non-path powers. So I'm just going to deal with the on-path here. Look at case 1 versus case 2. We're going to look at real mini circuits products. Jim Bain spoke yesterday. We're going to use some of Jim's products here from the data sheets, and you can see the amplifiers and gains are given. Using that cascaded formula I just showed you, we can see that case 1, which has an RF amplifier with a 2.7% efficiency compared to an amplifier with an 8.8% efficiency, almost 3 times, we can see that the waste factor is higher by almost 5 dB, right? And roughly the difference between 8.8 and 2.7. In other words, this is much less efficient by a factor of 3 than case 2, and that's because case 2 is using an amplifier with more efficiency. It's that last stage closest to the sink that matters. Let's look at case 3 and case 4 using a more efficient baseband and keeping the RF the same. Well, in this case, the baseband amplifier, you can see, is much more efficient. Here it's 4.8, and we go up to 14.2, a much more efficient baseband amplifier, almost factor 4. But you can see the total waste factor is virtually unchanged because that device way back near the source is divided by all the gains of the RF amp, and so it has negligible effect. In other words, we're able to see that the waste factor, the total consumed power of the path, divided by either the input times the gain or the output power, is a function of the entire source to sink, but the closest components to the source dominate. This is a beautiful theory because it now can be used to make decisions. And here's what's great about the waste factor compared to the noise factor. Noise factor was just for a linear cascade in a receiver generally. But this uses any kind of source to sink, including a passive channel or an attenuator. If you look at the math from source to sink, with the power being the signal out, being the attenuated signal, and if you consider the wasted power or non-signal being the power lost, you use the definition of waste factor, and what you can see is the total power consumed divided the total power out is simply equal to P1 over P2, which is the loss. In other words, you get the same result as a noise factor, with the attenuator loss being the noise factor. In waste factor theory, the waste factor is equal to the loss of an attenuator. This shows some of the duality involved in the mathematics. Very intuitive. And this also works for a radio channel, a channel with path loss, very powerful, which now allows mobile to base or device to device power consumption modeling for wireless architectures, the kind of systems that Eric builds at Ericsson. And he's now going to be able to use a unified theory to figure out the total power consumed at transmitters and receivers. By the way, in this paper we're going to make public, we've also looked at parallel change, MIMO, MISO, SIMO, so that you can apply this theory to parallel cascades going into a channel to get power loss. The waste factor of a channel is, again, just the total power consumed going into the channel divided by the output channel, which is going to be very, very weak. So the waste factor of a channel is equal to the loss of the channel, 1 over the gain. So when you do this, you can now define the waste factor of a transmitter. I'll show you an example that Huawei is doing to show the huge power gains we can get by making smart decisions with waste factor in a minute. But here we have a waste factor of a transmitter, a gain of an antenna. We have a wireless channel with a loss, and then we have a waste factor of a receiver, all computed by that cascaded formula. When you do this, you can use the cascaded formula for these 3 boxes as a cascaded chain from source to sink. Stage 1, the channel is stage 2, RX is stage 3. When you do that using the waste factor theory, you can write the system waste factor being the waste factor of the receiver divided by 1 over the gain of the channel, W minus 1, and so on, just using that cascaded formula. Here's the beauty of this approach. If the gain of the receiver, which is typically 80, 100, 110 dB, is less than the channel loss, typically 140, 150 dB at the cell edge. So when you have this case, this formula simplifies to simply being that the waste factor of the entire link is the loss of the channel plus the waste factor of the transmitter minus the gain of the receiver. We now have the key levers which matter most in power consumption. So it tells us that high receiver gain, high power efficiency, and a lower channel loss are desired. By the way, this shows, I can show you that small cells are much more power efficient over an entire square kilometer than large cells using this theory. Let's take a look now at different channels. I'll go through it quickly. Using this cascaded approach, we have increasing path loss leading to higher W. We see that in this case where we have a channel with minus 70 dB and minus 80 dB. The waste factor is about the loss in the channel. 10 dB increase means you are spending a lot more power, wasting a lot more power in case 2 over case 1. If you look at case 3 and case 4, we have a case where we're improving the transmitter waste factor, improving the power amplifier, or the last stages going into the channel. Here we have a transmitter with a gain of 61 dB, waste factor of 1 versus waste factor of 2. The waste factor of 2 is more lossy. We get 50% more power, 3 dB. We save half the power by using a more efficient transmitter. Makes sense, we all know it, but here's a theory that gives you exact numbers for comparison. And then case 5, look at case 5 compared to case 3. Here what we did is we boosted the receiver gain. The receiver gain went from 60 dB to 70 dB, and that gets us 10 dB back because the receiver gains increased. So now we know a definite theory that describes everything very easily. So just to sum up the first part, and I've got some really exciting results here in the end, the low noise amplifier from noise factor theory that Harold Fries gave us shows us that the LNA noise figure is the one that dominates the entire system noise. And therefore, you want to make the high gain low noise amplifier closest to the receiving antenna. We all know that. But in waste factor, here's what we have. The ADC will dominate the total system wasted power in a receiver because that's the device closest to the sink. And we know that when the channel loss is greater than the receiver gain, channel loss is going to dominate the waste factor. This is why I believe 5G and millimeter wave has been slow to take off. The carriers and the manufacturers have not seen the amazing power savings we get when we use directional antennas and close the link with a smaller channel gain. I'm going to show you in a minute how decisions I think are being made wrong. And with this approach, I think we can get things right. Here's what's done today in ETSI, ITU, 3GPP. All the global standards have an energy efficiency evaluation metric, all defined. These standards are all defined. They're used by carriers. They're used by vendors. These are looking at the performance metrics of energy efficiency. And I'm going to break all of these down, show you why all of them have problems and why the waste factor can be a replacement for all of these. But I just want to show they're looking at data rate, bits per joule or joule per bits consumed, and they all have their different approaches. Let's look at a RAN, a radio access network, from the energy generation on the far left to the infrastructure. This is the base station power supplies, air conditioning, lights, the main equipment, which is the base station and the antenna tower, then the channel, and then all the user equipment. And I'm using published standard results to analyze this. And Huawei has taken this to heart and is actually using this to identify the huge power savings we can do by using waste factor. So this is a RAN, a radio access network, and we're going to study these different metrics now and apply it. Right now, you can see that reference 1 at ITU gives an energy efficient metrics of a base station. It's the energy of the base station divided by the energy of the total consumed infrastructure. Reference 2 shows you that the energy efficient metrics for telecom equipment is standardized as the energy in the output signal over the energy of the whole base station consumed. And then energy of the radio is not even considering the channel. It's looking at the energy output. And here's what's interesting. Reference 4, NGMN, the next generation mobile network, simply multiplies each of these 3 energy metrics to determine its energy performance metric in bits per joule. This is done today. Now, when you look at that, I'm going to show you the problem with some of these metrics used by these different standards. Here's the ETSI standard. Let's consider radio unit A, a base station A. It has putting it into the waste factor lexicon. Non-path power is 50 watts. Path power consumption is 2 watt hours per gigabyte, and the data volume is 10 gigabytes. Okay, defining that by ETSI, you get a 0.14 gigabyte per watt hour energy efficiency using the current standard. I use now RUB. This is going to be a, and by the way, this was a more efficient base station. This is actually a more, this station A is a more efficient base station because you can see the power path consumption is only 2 watt hours per gigabyte. Let's use a legacy 4G base station. Non-path power also 50 watt hours. Path power is 4 watt hours per gigabyte. So it's less efficient. 4 watt hours is more power per gigabyte than the new 5G hardware. Yet it's loaded more heavily. It's legacy. And using the current metrics of today, you would think, using the metrics of ETSI, that this old 4G is more power efficient. At 0.2 gigabytes, you get more data per watt hour, right? But no, that's not true at all. It's traffic dependent. The 5G has not been loaded up. So it's sitting here and there's a lot of idle power being wasted, and that's not accounted in any of the metrics. Waste factor accounts for the non-path power as well as the path power. And the metrics today don't account for that non-path power. So the spoiler alert is waste factor shows you that the more efficient device is viewed to be less efficient in today's lexicon. Let's look at another one. This is now looking at NGMN. Let's look at network A and network B. Network A has older equipment. See, the user downlink is poor, but the EE, the energy efficiency metric used by ETSI, is high. So you think you're getting a lot of gigabytes per kilowatt hour on the low user downlink. But network B is better equipment. They paid more. It's 4 times more efficient, as Eric Wang said. 5G is much more power efficient with sleeps. And look at this. They have the same energy consumption. So the utility bill is about the same, but the metric says that 5G is much less efficient in gigabyte. It's because it's not loaded. So right now, if you're doing optimization as a carrier, it's a pretty amazing thing. Right now, the decision would be using the metrics today. You'd switch all your traffic over to site B, the less efficient. But if you switched it to site A, you get much more gigabytes per kilowatt hour, and waste factor solves this problem. I want to look at something else. Consider another radio unit, the power waste. This is another example, 500 watts being consumed. Radio unit B, it's got more non-signal power wasted, but the same total consumed power. When you do the math, what you find is that the energy efficiency of both these units will be the same using the ITU spec. Today, you'd think both base stations are equal, but when you use the waste factor, you find out that the new 5G is actually about 15–16% better. And I want to make a point. This is so important. When you look at the waste factor for these two devices, you see that one is clearly more power efficient than another. 15% power consumption, let me put that into perspective. A large carrier like AT&T or Verizon or T-Mobile has about 100 million customers paying about $80 a month. That's $100 billion in revenue. You can look it up, it's public. 2% of that, as Eric said, is their utility bill. They're paying $2 billion a year for power. All right. Figure there's about 400 or 500 carriers. Let's say 100 just for simple sake. Let's say 100 times 2 billion. So in a $10 trillion industry, we're seeing utility bills of $200 billion. Okay. So the carriers are paying $200 billion a year just to power the networks. It's actually probably higher than that. A 15% savings is $30 billion. And this is only 2% of the power footprint right now, 2 or 3%. Wireless being 2 or 3%. You look at the data centers, you look at anywhere there's information flow, we can save literally trillions of dollars if we start using metrics that consider the on-path and non-path power. This is very big. And here's the key, waste factor does not have a time varying or varying energy efficiency given power level. The whole idea of waste factor is you remove the dependence on input and output signal level. So you can see the waste factor is constant. And finally, I just want to show you we can use waste factor to find in the RAN network the key components that we can dial down. Turns out that a base station is about 3 to 4 in waste factor, and a mobile unit is about 18 to 25. Turns out the mobile unit's not very important. So to summarize, we can now use waste factor as a metric. And when the metric waste factor is low, that's good. There's less waste. So when it's low and the data rate's low, we can use it for carriers and equipment makers to increase transmit power, increase the bandwidth, carrier aggregation. If you have a low waste factor and a high data rate, that's optimal. If you have a high data rate but high waste factor, you can now optimize the scheduled transmit power, turning things on and off, as Eric talked about. And then when the waste factor is high and the data rate's low, that's bad. You need small cells. You need more efficient hardware with better W. You need to invest in CapEx. And so this is really a powerful metric just to show you that we can start using this in decision making. And these show you kind of the key aspects of what a carrier can do to save the electricity bill and ultimately save the planet. We're talking about sustainability, and this is a big deal. Looking at another way, let's look at the consumed power, the utility bill and waste factor. If it's low waste factor and low consumed power, that's optimal. If it's low consumed power but high waste factor, that means we've got inefficient energy transmission. We can place the radio unit or go to smaller cells for a lower W. Low W and high consumed power means that we need to focus on the non-path consumption, shutdown. And then finally, adopt power domain. If we have high waste factor and high consumed power, we're in bad shape. We need to do power domain savings. We need to replace the equipment with smaller W. W should be on the spec sheet, I think, of any device that's going to be used in a source distinct information. So to summarize, I think this is powerful for AI and ML. We could do training. We can do smart decisions. There's a lot of things we can do with it. So here's a figure of merit, waste factor. We can start using it. It's analogous to the noise factor. It allows us to assess power efficiency. So many applications. And with that, I want to thank you.
So thank you very much for this very interesting talk. I am sure that we will find the waste factor in the textbook, in that coming textbook. So we have some questions for the speakers. So let me read some of them from the chat. There is one that says that we already have efficiency defined. So then why we need another factor as waste factor?
I just showed you. I just showed you why. The reason why is that the efficiency factors defined to date are not using the subtleties of on-path and non-path power. So you're hiding the actual information power efficiency in any network. That's hidden today. That's what I tried to show you. These metrics that are adopted are morphing in and combining the on-path and non-path power. You can't figure out where the wasted power is on the signal path or where the wasted path power is just to keep the air conditioning running. And when you don't break that down, you can't figure out how to make more efficient networks. So this is a more granular approach that is standardized and can be used in any cascade. That's why.
Okay. So then another question says that, do you think that, which are your thoughts about the waste factor being a regulatory requirement in the future?
I think it could be standardized. I think noise figure is not a regulatory requirement, and it's not in the standard. Waste factor could be the same way. I think each vendor could offer a waste factor for their transmitter. I think every device made, an amplifier, can have a waste factor and a noise figure. I'm really interested to see, as device makers and researchers get into this, how waste factor and noise factor counterplay with each other. I mean, this is a parameter that's very fundamental and can be used in a cascaded system, and it makes analysis and optimization much easier. It provides a model, a way forward that breaks out all the path components, going back to the fundamentals of power superposition.
Okay, and this the last question, because we don't want to to make you a lot of questions. So says, for this waste power, could you comment on how to consider multi-bin or multi-user system?
Yep, yeah, we're publishing that I'm looking at the paper today. We're going to submit it shortly. I'll make it open on ArchiveX. It turns out you can use these same ideas, and then you do combining, either coherent or non-coherent. So if you have multiple paths, they'll either coherently combine, where the phases are aligned, it's like coherent MIMO, or you can have non-coherent combining. So you basically take these ideas of waste factor cascaded and then look at the sum of the powers. And remember, waste factor is not a function of the power level. That's the beauty of waste factor, and that's a problem with all the carrier metrics in the global standards. They're all, when you dig down in, they're all a function of the traffic load, or the resource blocks used, or the transmit power level used, and that's all a function of input-output power. Waste factor removes that. If you're in a linear system, and that's why we have OFDM power backoff, to try to keep it linear. If we're in a linear system, you should not have a power efficiency that depends on input or output. Similarly, when you have parallel paths, it should not depend on the actual power levels, but just the relative weightings. And so that's the theory we'll present.